Alright, so we're going to spend a little bit of time discussing rational exponents. So let's just give ourselves a definition of what a rational exponent is. Okay, so you've heard the word rational before, and you've heard the word that's inside of rational, this word right here called a ratio. And a ratio is just another way of describing a fraction when we're comparing two numbers. Right? And so in this case, when we're talking about rational exponents, it literally just means that we're going to have exponents now that are fractions or decimals or some other way of writing parts of a whole. And so there's actually a direct connection between a rational exponent and a radical expression. Okay, and here's what that connection is. The denominator of the simplified rational exponent, it becomes the index of the radical expression. Okay, and so for these problems, at least to start, we're going to assume that the numerator of all of our fraction exponents is 1. And so if that's the case, if you take a look at this example here with 27, I'm claiming that if you raise 27 to the 1/3 power, right, here's what ends up happening. Okay, we're starting off on the left-hand side with a denominator of 3. Okay, and that denominator of 3 becomes the index of my radical, which means on the right-hand side, when I'm asking the question, what number do I have to raise to the 3rd power to get 27? Okay, I'm actually asking the same question over here. I'm actually saying when I say 27 to the 1/3, I'm asking the question, what number do I have to raise to the 3rd power to get 27? They mean identical things. Okay, and so if you want to know where that 1 is coming into play, why that's not showing up anywhere on the right-hand side, technically the 27 is actually being raised to the 1st power. We don't see exponents of 1. So you can start to get an insight into where this numerator is going to come into play. It's actually going to be a normal old exponent either inside or outside of the radical. Okay, but we'll talk more about that in a second. Okay, so down here I just have a quick explanation about why these things why they mean the same thing. Okay, if I were to perform an operation on the left-hand side and say let's cube 27 to the 1/3, what we know is that when I'm raising a base like 27 to a power, and then I raise that to another power, that I can combine those just by taking the 3 and the 1/3 and multiplying them together. And so what I ended up getting is 27 to the 1st power. Okay, and on the right-hand side, we actually get the same thing happening. If I cube something that has a radical index of 3, they cancel each other out, and I also end up with 27. Right? And if you were to try this for any arbitrary expression where the left-hand side and the right-hand side are equivalent, where the denominator on the left is the index on the right, and you were to try to do this, it would work for any expression at all. So performing operations on these two different versions of the same thing gives you the same answer, right? So we could actually prove that if we wanted to. All right, so let's start off just by looking at some radical expressions using different index numbers and seeing what they would look like in their exponential form. Okay, so remember, the number on the inside, in this case x, right, is going to become the base, and the index on the outside, which in this case is 4, that is going to become the denominator, okay, of my base. Okay, so in this case I don't see any other numbers floating around, so I'm just going to put a 1 on the top, and so I'm claiming that the 4th root of x is the same as x to the 1/4 power. And so when I come over here to the right, we're going to do the same thing, and we're going to start to see what happens when there is a number floating around, another exponent like 5. Okay, so what I'm going to do is I'm going to do the same thing. I'm going to say y to the 5th. That's what's underneath my radical. That's my radicand. Okay, I'm going to raise that to my index becomes my denominator. Okay, and I'm going to put a 1 on the top. And we just spoke about what we do when I raise something that has a power to another power. We can multiply them together. And so what I'll end up with is 5 times a third is 5/3, right? And so you can see again, here's where that connection's starting to come in. The exponent of the radicand, in this case the 5, becomes the numerator when I put it in its exponent form, right? So the index on the outside is the denominator, and if there are any exponents on the inside, that becomes the numerator. Okay, so let's try the other direction. How do we convert from an exponent form where there are fraction exponents back into its radical form? So it's going to be very similar. So I'm going to say, remember, the 3 on the outside becomes the index of my radical. Okay, nothing on the top, so I'm just going to leave that alone. Okay, we're not going to see that show up. And then the base of my exponent becomes the radicand, the number on the inside of my radical expression. Okay, so I can do that for each of these, and we're going to actually do an extra step of simplifying for the other ones. Cube root of 4 doesn't really simplify nicely, but if I take a look at this next one, this one says, again, exponent on the outside becomes the index. Okay, And so remember that an index of 2 really just means to square root. And so I'm really asking here, what's the square root of 16, which we know is 4. And I can do the same thing with 81. Right? 81 is the fourth root. 81 to the 1/4 is the fourth root of 81. And remember, what this question is asking is, what number do I raise to the fourth power to get an 81? And you might just have to guess and check at the beginning without a calculator. But if we do 2 to the fourth, well, 2 to the fourth is 2 times 2 times 2 times 2, and that's 16, so that's not it. Well, let's check 3. 3 to the fourth is 3 times 3 times 3 times 3. That is 81. You can check that. So the answer to their question, what do you raise to the fourth power to get an 81? The answer is 3. Okay, so we can apply this to slightly more advanced concepts, like, for example, problems that have numerators other than 1, or problems that have decimals, or problems that, maybe there's 2 fractions, right? So if the numerator is anything other than 1, we're going to break it into 2 exponent parts and deal with them separately, right? So for this first example, I'm going to show you 2 different ways that we could achieve this same exact answer. Okay, so we're going to start off and we're going to break this up, and we're going to say, well, what happens if I do 27, okay, to the 1/3 squared, right? So again, the exponent from the numerator of my fraction becomes just a regular old exponent in my expression. So 27 to the 1/3 really means the same thing as the cube root of 27. Again, it's being squared. And the cube root of 27 says, what number do you cube to get a 27? Well, that would be 3 squared, and that looks like 9. Okay, so 27 to the 2/3 power is the same thing as 9. Okay, so we can think about this same thing, this 2/3, a different way. We could say maybe that exponent, that 2, is actually on the inside of the radical with the 27 instead of being on the outside of the radical after we cube root. So maybe it'll look like this instead. We'll say 27 to the second power, and then we'll cube root. Okay? And if you see what changes in my second step, the only thing that changes is now that exponent of 2, okay, is going to be on the inside. Now this says 27 squared, then take the cube root. But guess what ends up happening? Okay? In this case, 27 squared is the cube root of 729. Okay? The cube root of 729. And if you take the cube root of 729, you also get 9. Right? So if you notice, it didn't matter if I decided to attach the numerator directly to the base. Do that first, right? Like we did over here. First we said, let's square first, then raise to the 1/3. Over in the other one, I decided, well, 1/3 times 2 can work the other way too. I can cube root first, then square. I got to the same answer. And so the question is, well, which way should you do this? And the answer is, whichever way makes your life easier. There isn't one specific way to do it. They're both correct. For this particular problem, I would probably go with this first one, because if you notice, what happened is I made the number smaller before I squared and made it bigger. So finding the square root of the cube root of 27 and squaring 3 is easier than squaring 27 and then having to find the cube root of a big number like 729, right? So in that case, I just chose, I would have chose the blue one and said that looks a little bit easier for me to handle. Okay, so let's do the same thing with 16 to the 3/4. 16 to the 3/4. Okay, excuse my writing. All right, so let's try this. So 16 to the 3/4, we're going to say that's the same as 16 to the 1/4. Okay, and 16 to the 1/4 we're going to cube. So 16 to the 1/4 power is what number do I raise to the 4th power to get 16, or in other words, the 4th root of 16. And then we're going to cube that answer. Well, the 4th root of 16 is 2, because 2 to the 4th power is 16, 2 cubed, which is 8. Okay? So there's another simple example of where we just split the numerator off, took the 4th root, and then we applied the cube afterwards. So it's actually like 2 problems in one. Okay, so let's take a look at this 4 to the 2.5. So it's like now, well, I mean, decimals like 2.5, those are also like fractions. So we should be able to handle problems like this. And so for a problem like this, we actually just need to look at it and say, okay, 2.5, how do I write that as a fraction? And so 2.5, if you check, is the same as 25 over 10. So this really means the same as 4 to the 25 over 10, right? Because this is a tenths place, right? And I can reduce 25 over 10 and say this is the same as 4 to the, if I divide the top by 5 and the bottom by 5, 5 over 2, right? And then this means 4 to the 1/2 to the 5th power. And now 4 to the 1/2 is the same as the square root of 4 to the 5th power. Well, the square root of 4 is 2 to the 5th power, and that is 32. Okay, so we're going to say that this is 32. So even if we have decimals, we're just going to convert those decimals into a fraction form, and then once they're in their fraction form, we can do what we've done in the past. Okay, so let's take a look at one more problem. Hey, we're not going to do this 3/7 problem. We'll stop at t. Okay, so this t to the 1/4 and t to the 2/3, it's like, okay, now how do I handle this if I want to put it in radical form? Well, the first thing we can do is apply our exponent rules and say, if they have the same base, right, in this case they do, they both have a t, okay, I'm going to add together my exponents. So I need to add together 1/4 plus 2/3. And so to add together fractions, it looks like I need to have the same denominator, which in this case would be 12, right? And so I need to multiply, it looks like, the bottom by 3, so the top by 3. And then the same thing over here, I'm going to multiply the bottom by 4, so the top by 4. So instead of using 2/3 and 1/4, I'm going to use these new exponents. And so when I add them together, it's t to the 11 over 12. And if I want this to be in radical form at the end, the most I could do here is say that this is now the 12th root, okay, of t to the 11th power, right? And this would be a simplified way of writing the product of these two expressions.